Now I'm more interested in the distinction between the Newtonian orbits and the Einstein orbits, okay, or trajectories. We all know that in Newtonian theory reproduces Kepler's orbits. It's a famous result. And we are interested in knowing what kind of modifications Einstein's general relativity will do to these trajectories. Now, Newtonian trajectory, let me give you a reminder. There exist open trajectories, right? There exist open trajectories, which are for epsilon greater than equals 1. Let me go back to the Mathematica file here. As I was mentioning, if your energy is larger than this, or outside this potential well, then of course orbits are open. So let me get back to the presentation. Yes, these are open. So let me just draw some kind of potential, which goes to infinity here. If your energy is above this potential well, then this is an open orbit. So the particle will come in and go out, that's all the way to infinity. And these are parabola or hyperbola, parabolic or hyperbolic. And if the energy is less than or inside this potential well, then the orbit will be closed, because motion will be confined entirely to this region, back and forth between the maximum of r and minimum of r, and for which epsilon should be less than 1. The circular orbit lies at the bottom of the well. The bottom of the well, there is no freedom to even change r, so that would obviously mean it's a circular orbit, and that radius of the circular orbit, given that angular momentum or specific angular momentum h, is given by this formula. You can derive this yourself and check for yourself. So what I want to highlight, the reason I have this formula on the slide is that it tells you no matter how small h is, you can always find a stable circular orbit. Okay, circular orbit will always be there. So this RC exists for all values of h. There's no restriction, and this is going to change in Einstein theory. In Newton's theory, you can have circular orbits for arbitrary angular momentum, no matter how small. On the other hand, in Einstein theory, you will see there is a threshold below which there are no stable circular orbits. All right, as I was mentioning, no stable bound orbits for angular momentum less than this threshold value. 2 times square root of 3 times g Newton times m. Okay, so if your h is less than, if the specific angular momentum is less than the threshold value, there's no stable orbit. And the reason is that the minima disappears. Let me go back to the Mathematica file. Let's say if I lower the value of the angular momentum, which is in the first term, remember h is here. So let me lower the centrifugal barrier by making it something like 1000. And as you can see, maybe 2000 is better. Yes. The Newtonian gravity plot, potential plot did not change. You still have a minima here. And then you have the centrifugal barrier. On the other hand, the Einstein curve, the potential just goes below. There is no centrifugal barrier at all. Okay. As a result, there is no bound orbit. There is no bound orbit. Okay, no stable orbit. If you want this minima, you got to have. If you want circular orbit, you must have this minima, which is there in the Newtonian potential plot. In the Einstein potential, we don't have a minima. It just keeps going downwards. So we lose that feature. You only have the minima when you have a certain amount of angular momentum. Now I increase the angular momentum and you get back this minimum. Okay. As a result, there is a potential well, but the potential well will disappear if you lower the value of h. Just now I lowered it and you see that it disappeared. Okay, let me go back to the presentation. So the potential has no minima if you lower h below this, and this is left as a homework exercise. Please do this. As a result, if you leave a point particle, if you have a point particle moving with less than the threshold of angular momentum, it will just spiral down and crash into the center of the star. So in Einstein theory, stable circular orbit only appear for a critical radius as well. So when r is greater than 6 times g Newton times m, remember this is twice g Newton m is the Schwarzschild radius, so this is actually 3 times the Schwarzschild radius. SCH. Let me write so this is thrice. So you only have stable circular orbits for this value. Okay, 3 times the Schwarzschild radius or 6 times G Newton. If you're less, you cannot have a circular orbit less than this. Okay, again, this will be left as a homework exercise to prove that the stable circular orbit, there is a minimum radius. Okay, you cannot have stable orbits arbitrarily close to the star. Okay, if you come too close to the star, there are no stable orbits. And what is the critical distance? That is sometimes known as R ISCO, R subscript ISCO, where ISCO is a short form for innermost stable circular orbit. Okay, so that is 6 times G Newton times m, or 3 times the Schwarzschild radius. Between the star and between R ISCO, you cannot have any stable circular orbit. It will always crash down into the center. All right, let's look at the shape of the orbits. Okay, let's look at the shape of the orbit. And as I mentioned previously, in Einstein theory, because the Laplace-Runge-Lens vector is not conserved, the major axis, not the semi-major, I'm sorry, this is a typo. The major axis will rotate. And if the major axis rotates, then we know that the bound orbits will not be closed. So let me just draw what I mean. So this is the equatorial plane. And let's say the particle starts rotating. Initially, it will be an elliptical, but this ellipse will not close, and the particle will keep making orbits like this. So the orbit is not going to be closed, okay, because the major axis will keep shifting. In fact, major axis rotates. So the major axis will rotate. So the whole ellipse will also rotate along with the major axis. Okay, so we will demonstrate that. So we will determine the shape of the orbit by treating general relativistic effects as a perturbation. Remember, every time I'm writing the equation, I'm distinguishing the Newtonian part in black fonts and the general relativistic correction in red fonts. Now we will first show that the general relativity term is actually much smaller compared to the Newtonian term, so we can treat it as a perturbation. And then we will only work in leading order in the post-Newtonian or general relativistic correction. So, as I said, we are interested in the orbit. So we are not solving for r as a function of tau, but the shape of the orbit is given by r as a function of the azimuthal angle on the plane. So for that, again, we appeal to the velocity constraint, which I've written here. And if you divide both sides by phi dot square, then you get this equation. All right? This is the equation inside the box. And now we replace this. Remember, this is r dot over phi dot. R dot over phi dot, which is dr d tau over d phi d tau. The d taus cancel, and we can replace it as dr d phi. So r dot over phi dot is nothing but dr d phi. And also t dot square. And phi dot square we can replace using this angles of motion in this equation. So let's make all these substitutions on this in this equation, and we get the equation at the bottom of the slide. This is the same equation as this one, except I have taken this ratio as dr d phi, and then 1 over phi square and t dot square and phi dot square we have substituted in terms of the conserved charges. So we get this equation. All right. So finally, we use Newton's trick, in which, if you remember how Newton worked out the shape of orbit, he substituted 1 over r to be u, and then solve for the u, which is easier to solve. So the substitution we will make, u is 1 over r, and then we will rewrite the velocity constraint which we had in the last slide, this box equation. In terms of u, it will turn out to be this. And then further, if you want to get a second order equation instead of a first order, we can take a phi derivative of both sides, which I've done here, as you can see. Again, the second order derivative of u in terms of phi, compared to the Newtonian theory, this has an extra piece. Okay, there is an analogous equation in Newton's theory as well, and those terms I've expressed in black fonts, the first 3. And if you turn on general relativistic corrections, then we get an extra term, which I've demarcated in red fonts. minus 3 g Newton m times u. Now, they mentioned that this extra term, minus 3 g Newton mu, which I've denoted, or not without the minus sign, this term I've denoted by delta, and it will serve as a perturbation parameter. And this will serve as a perturbation parameter because it is dimensionless in units of c equal to 1. If you are working with SI units, then you have to define it by dividing it by c squared. But let's say I'm persisting with c equals 1 units, in which this ugly factor of z squared, pc squared is not there, and I can treat this delta as a perturbation. Of course, I have to justify and show that indeed this is the case. And as a test case, I will take our solar system. So delta is proportional to u, so delta will be maximum when u is minimum. And because u is 1 over r, when u is maximum, that means r is minimum. So we got to look for the minimum value of r. And the minimum value of r is usually realized for the innermost planet. Okay, so if we find this, the largest or the upper limit of delta comes from the innermost planet. So for the solar system, the innermost planet is Mercury. So we can substitute in delta g Newton, which is this in SI units, m as the solar mass, which is 10 to the 30 in SI units. And for u, I'm going to use u of Mercury, which is 10 to the minus 10 meters. Remember, Mercury is around 10 to the 10 meters from the sun. So 1 over r is 10 to the minus 10 meters. And I'm going to substitute here in the formula for delta, which I've done here, for Mercury, and it turns out to be 10 to the minus 7. So the largest value of delta, remember this is the upper limit on delta. The largest value of delta is 10 to the minus 7, which is a ridiculously small number, and hence analysis of this equation via perturbation theory makes sense. It is justifiable because this number, this correction to 1 is, this is 1 in Newton's theory minus 10 to the minus 7. And this is the upper limit of delta, and not even the general possible value of delta. Remember, for further planets, u will be even less, by orders of magnitude less, and hence it will become even less in comparison to 1. So the largest possible value will be, or this generalistic correction will become significant only for the innermost planet. Even there, we see it's very small, 10 to the minus 7. So a perturbative analysis is in order. So let's do the perturbative analysis. So in this equation, in the second order equation which we have written here, this equation I will substitute perturbative ansatz. That is, u will be written in these kind of functions, u0 of phi, u1 of phi plus u2 of phi, and un of phi will be taken to be order delta to the n raised to the n. So nth order in delta with some numerical coefficient. That's why I've written the similarity sign. That means, of course, there is a coefficient, dimensionless coefficient, which we have to determine in order to determine the solution. Okay. So you can think of u raised to the n as the nth order in delta. Okay, and we will take this perturbation series and feed it to the equation and then solve order by order in delta. So at leading order, of course, we will get back Newton's theory because the correction is order delta, which is in GR. So we will get this u0 will obey this Newtonian equation. And the solution to this is known from your undergrad classes. You can recognize this will give you conic sections. So the orbits are conic sections. Sorry about that. In the box, as you can see. So this parameter, so this is the second order equation. So there'll be two constants of integration. The first constant E is the eccentricity of the conic section, which is given by this formula. Just a refresher from your undergrad course, psi is the specific energy, h is the specific angular momentum, and of course m is the mass of the central planet, a central star, which is creating this gravitational field. So the eccentricity of the conic section can be determined from that. And the second constant of integration is phi of p, or phi of p, which is the perihelion. So when phi is phi p, the argument of the cosine vanishes and the cosine takes maximum value. So that means u will take maximum value. And because u is 1 over r, when u takes a maximum value, that means r is smallest, minimum, That is the point of closest approach to the central object. So this is the perihelion, location of the perihelion. In most textbooks, I think they set it to 0 by convention. You can always choose your major axis such that the perihelion coincides with the major axis. I'm sorry, not with the major axis. Perihelion is of course on the major axis, but the major axis coincides with the x-axis. Now at subleading order, so this was at leading order. At subleading order, we obtain this equation. If you look at the left-hand side, this is the equation of an oscillator with unit natural frequency, second derivative plus something proportional to the force, restoring force, plus restoring force with the spring constant K1, so unit natural frequency. And the right-hand side, there is a source, and U, we know it's a 1 plus cosine, so it's a periodic function, and square of that is also a periodic function. So we basically have that of a forced oscillator with the forcing function being a periodic function. Okay, so this is the forcing function. This type of equation you have already solved in the undergrad. There's not much complicated. You can plug it directly in Mathematica and also obtain the solution. That way it's easier. But if you analytically, of course, you recognize this is the forced harmonic oscillator, and the writing down the solution is very easy. So let me write down the solution. The solution looks like something like this. Okay, given the zeroth order solution, like the first order solution looks something like this. So you will see there's instead of the cosine, you have a sine argument, and this prefactor is there. There's a term which is proportional to the eccentricity, and then there is a curious factor of psi, and the psi is defined here. Okay, psi is 3 times some dimensionless number times phi, the azimuthal angle. Okay, so this is the first order solution. And as I said, for all intents and purposes, the first order term itself is so small, we will not bother about the second order and all other higher orders. Okay, we will be content with the zeroth order and the leading order correction. So let me add them up to get the full solution. I should have had approximately instead of equal to, because I'm ignoring all the higher order, because already the leading order term, as I said, in comparison to the leading order, the correction is 10 to the minus 7. It's very weak, so there's no point taking further higher order. We will be content with just considering the first zeroth order and the leading order correction, U1. So if you combine them, because of the fact that this number is very small, psi is very close to 0. As a result, U0 and U1, so let me just point out, U0 and U1 can be added using trigonometric identities. And the closed form solution, which actually Einstein obtained in his 1916 publication, is something like this. Okay, so this looks exactly like U0. That's why I've written in black fonts. This looks exactly like the Newton solution, which is this, except the argument of the cosine has changed. The argument of cosine, instead of phi minus phi p, you have phi minus phi p minus psi, where psi is this, whatever. Highlighted in purple fonts. Okay, so it's the same as exactly as the Newton solution, except the argument of the cosine has changed to psi, phi minus phi p minus psi. Okay, so how does it lead to the fact that the major axis will rotate? Let's look at that. So it will turn out that the perihelion will shift every period, and it will shift in a rotation. It will rotate basically. It could have shifted in an arbitrary way, but no, it will actually rotate. We will show that. So what is the azimuthal angle difference between two successive perihelia? If the ellipse or the conic section was not rotating, we would have, if the first perihelia appears at phi equal to 0, then after one full revolution, when it comes phi changes by 2 pi, we will get that perihelia. So the change in phi between two successive perihelia is twice of pi. So this is the definition of perihelia. And in case of Einstein's theory, the criteria is exactly the same, because all we demand is that whatever is the argument of the cosine, that should change by twice of pi. Why? Because u will be minimum U will be maximum when argument of cos is 0. And so the first perihelia, let's say, is at phi equal to phi p. The second perihelia will also be at the point such that the cosine argument of the cosine is twice of pi. So between two successive perihelia, the argument of the cosine phi should change by twice of pi. And the argument of cosine of phi is this now, okay, in Einstein theory. So difference in the argument of the cosine must be equal to twice of pi. Now this delta of phi p is 0 because phi p is the constant of integration. So if I take variation difference, it will be 0 because the constant of integration doesn't change. On the other hand, phi and psi are not constants of integration; they are functions, so we need to consider them. That's why in the second equation, second step, I've got rid of phi p. Now psi I can substitute in terms of phi p, whatever psi is. Sorry, not phi p, phi, which is this. And then this condition tells us that the change in the azimuthal angle when between two successive perihelion is given by twice pi divided by this quantity. So when we combine these two, I will get 1 minus, and then I bring it, transpose it on the right hand side in the denominator, and we get the azimuthal change between two successive perihelia is delta phi, which is twice pi divided by this. Now this quantity is much less than 1 in the denominator, 1 minus something less than 1. I can always expand in a binomial expansion. And then we get twice pi plus some positive quantity. What does it mean? Well, it means that instead of twice pi, the perihelion between two successive perihelion, in order to reach the second perihelion, we need to go beyond 2 pi. So let me again draw the ellipse. So this is the first perihelion, and when it approaches the perihelion for the second time, it has to go not 2 pi but somewhere more than 2 pi, somewhere here. So this angle is now, so let me draw this angle. So this angle is more than 2 pi. So okay, sorry, this angle from initial to final. Initially it was here, and the second perihelion appears instead of here, it is here. So the azimuthal angle has to increase by more than twice of pi. Sorry about that. Okay, so this is sometimes called the azimuthal excess. So h square, I'm going to substitute in terms of the usual conic section parameter, in particular for the ellipse. So A is the semi-major axis, and E is the eccentricity. In terms of those two, the specific angular momentum squared can be written, and then I can substitute it here, and then the perihelion excess, because it is more than twice of pi. So because the orbit is rotating, the perihelion next second time between two successive perihelion, the azimuthal angle has to be crossed by more than twice of pi. Okay, not just twice of pi. In Newton's theory, it would be just twice pi, but in Einstein's theory, is more than twice of pi. So this azimuthal angle excess over twice of pi, this quantity is very important, and this is been demarcated in red. But after the substitutions, this I can write in terms of the orbit parameters, that is the major axis, semi-major axis, and eccentricity, and mass of the central object, so on and so forth. And I've also brought back c squared because I'm using SI units. Okay, so this can be computed using Einstein theory, and in fact, it accounted for the observed perihelion excess of Mercury, which had been observed in 1859 actually. The perihelion excess from Mercury had been observed in 1859, and for half a century there was no explanation. Newton's theory could not account for this. People tried very hard, including ideas such as there might be a third planet, there might be another planet between Sun and Mercury, which is causing this deviation from this Newtonian or Kepler orbits, but that planet was never found, and so it remained unexplained for half a century till Einstein came along in 1916 when he put forward the general relativity paper. He also showed that Einstein's GR correction can account for that observed perihelion excess of Mercury, which is 43 arc seconds per century. Of course, for one revolution, this perihelion excess is small, so it is not noticeable. But if you wait around for 1 century, then the accumulated perihelion excess will be significant enough to be observed by telescopes at the time, and it was 43 arcseconds per century. Okay, per century, and Einstein's actually in this paper derived this formula and then plugged in all the known values for the orbit of Mercury, and this turns out to be 43 arcs per century. And this is considered to be one of the classic tests of GR. This is not a prediction, this is actually a post-prediction because the data already existed, and Einstein came along and in general relativity explained this data, which could not be explained by Newtonian theory. And it is considered to be one of the 4 classic tests of general relativity. We've already talked about gravitational time dilation and gravitational redshifting as one of the first classic tests of general relativity done by Pound and Repka. And today we learned about the second classic test of general relativity, which is the perihelion excess for Mercury. Now, I just want to add a little bit of qualifier that actually Newton's theory can explain the perihelion excess if you give up on the idea that the sun is a spherical object. Now, as you know, spherical object has 0 quadrupole moment. But let's say the sun is not a perfect sphere, just like the Earth is. We know the Earth is oblate spheroid. Maybe the sun is oblate spheroid or prolate spheroid. In that case, the quadrupole moment will not be 0. And one can show if you have if you do the multipole expansion, the quadrupole term, if you assume that the sun is not perfect sphere and it has a non-vanishing quadrupole moment, that quadrupole term can indeed lead to a precession of the perihelion of Newtonian orbit as well. So actually it's not completely honest to say that Newton's theory cannot account for the perihelion axis. The better thing to say is that at that time people didn't have any data about what the shape of the sun is at the early part of the 20th century, so they assume it's a perfect sphere, and then it has no quadrupole. But later on, people thought about it and came to the conclusion that this is not the right conclusion. Maybe we should look for we should find a way to measure the quadrupole moment of the sun. And later on, I think in the 1950s or 60s, sometimes they figured out that the sun indeed has a very small quadrupole moment, so it's very close to an exact sphere. And as a result, it cannot cause a perturbation of Mercury's orbit enough to explain this perihelion excess. So only general relativity can account for the perihelion excess, and not Newton's theory, with the assumption that the sun has a non-vanishing quadrupole moment. All right. With that, we are done with our lecture agenda, and let's provide a summary and an outlook for today's lecture. So we examined time-like geodesics in the Schwarzschild geometry because we wanted to know about motion of planets and comets around the sun, around a spherical object like the sun. And the way we did the analysis is first we identified 2 killing vectors, which led to 2 first integrals or conserved charges. And then using these conserved charges, we solved the radial equation using the velocity constraint. Okay. With radial geodesic equation, we did not directly use. Instead, we used the constraint that these geodesics must be time-like, which leads to the velocity constraint. And the velocity constraint gives you a first-order differential equation, which can be readily integrated, which we did. Then we looked at the shape of the planetary orbits to first post-Newtonian order. That is, as I've shown, that the orbits, the correction can be thought of as a perturbation. And first order is called the first post-Newtonian order. And that led to the perihelion precession, that the fact that the Laplace-Runge-Lenz vector is not conserved in Einstein theory, but it is in Newton's theory, leads to the fact that the conic section will rotate. And this will lead to the azimuthal excess, which we wrote down for Mercury. And that is considered to be one of the 4 classic tests of general relativity. Now, in the next lecture, we will look at motion of light instead of point masses, light in the Schwarzschild geometry, which will lead us to examine light-like geodesics. And that will lead to another couple of classic tests of general relativity, namely gravitational bending of light or gravitational deflection of light, and gravitational retardation of light, or better known as Shapiro radar echo delay. So with that, I'll conclude the lecture here. Thank you very much for your attention, and I will see you next time.